Okay, good morning, everyone. So I'm in a different venue today, so I'm in my office. And I hope things go okay. Before we begin, any questions? Okay, I will begin. Right, so today we're going to finish up calculus, and then we're going to start talking about geometry. So to finish up calculus, we're going to talk about precisely the relationship between two versions of differentiability that one we have been talking about, which are functions of class CK. And I will do this. Okay, and then this, as we're going to define shortly, is the version of differentiability that you're familiar with from, say, a multivariable calculus course. And those definitions can be extended to normed spaces. Okay, so the first thing I'm going to do is give a precise definition of this class of mappings, FCK. Although we've talked about them frequently, but just to say something precise. Okay. All right, so the setup is the usual one. We have locally convex spaces, U and V. We have an open set in U, and we have a mapping phi from O into V. Okay. Okay, so I'm going to say, so I'm going to have a list of definitions here. So the first thing is the mapping phi is Frechet. So the F here stands for Frechet, and Frechet derivative is the derivative that you know about already. Okay, so that's what it's called, is the Frechet derivative. And just so you know, the derivative, the directional derivative that we've been talking about, that's often called the Gateau derivative. And so there's two kinds of differentiability, Frechet and Gateau. And what we're going to do today is talk about those when the locally convex spaces are normed. And in fact, sorry. I meant to say norm spaces. The discussion today for CK and FCK applies to norm spaces. So these are normed spaces. Okay, so U and V are normed spaces. And we'll say that the mapping phi is Frechet differentiable at a point x naught in O if, okay, there exists a linear mapping, which is the derivative, and I'm going to give it this particular notation. I'm going to call it f d phi for Frechet derivative. Okay. Excuse me. Of x naught. Continuous linear mapping from U to V such that, okay. And so the way I've talked about this, when I've talked about it loosely before, is I've sort of said that the approximation of phi by its first derivative, by essentially what amounts to the zeroth and first order terms in the Taylor series, that approximation is good. And I'm going to say that in a slightly different way, although it's pretty clearly equivalent, such that the remainder, okay, so the remainder is the function minus the zeroth and first order Taylor terms, right? So that's, and I'm going to call this R phi x naught. Okay, so this is going to be a mapping from O minus x naught. So I'm basically just shifting everything by x naught into V. And this thing is defined as follows. So it's going to take a point X in O, and it's going to map it to phi of X naught plus X minus phi of X naught minus F d phi of, sorry, I'm going to move this over a little bit. Okay. Of X, okay. Sorry, X naught. Okay, so what I know is that this is a continuous linear mapping from U to V, and I'm going to apply this continuous linear mapping to X, right? And so you can see here, if you want to think of X here as being small, right? Because X is a point which when X is 0, that corresponds to the point X naught, okay? Okay, so that's the remainder, such that the remainder satisfies. Okay. That the limit as x goes to 0, remainder divided by the norm equals 0. Okay, so this is exactly the definition that we gave before. The only difference here is that I'm spelling out the remainder. Okay. So that gives me differentiability at a point. Right? Then phi is Frechet differentiable. If it's Frechet differentiable at every point. As usual. Okay, so notice that the derivative here is not a derivative in a direction, as we have talked about for mappings of, say, class C1. Okay. Right, and phi is continuously Frechet differentiable. If if it's Frechet differential, of course. And if the mapping FD V, which now is going to be a mapping from O into the space of continuous linear mappings from U to V. Okay, so keep in mind that one of the issues when you're working with spaces that are not normed is that this space does not have a natural topology. Okay, but because the space is normed, it does have a natural topology, and okay, and that topology, I'll just sort of do, okay, put the operator on. E, U, V, which we had defined before. Okay. If this mapping is continuous. And just to not have to write out the laborious expression continuously Frechet differentiable, we'll also say phi is class FC1, like so. Okay. All right. So these notions I've made reference to before, and I've even written them down and reasonably carefully defined them. So there's nothing new that we've done here. Let me also define higher differentiability, which again I have done before. Okay. And so okay, so phi is, and the definition I'm going to give is the usual, is the recursive definition, similar to the one that we used for class CK functions. Okay, so I'm going to say that phi is of class FCK F if phi is of class C1 FC1 and its derivative f d phi is of class C, FC, FC, K minus 1, F. Okay, so this definition is exactly analogous to the definition of higher order differentiability that we've been using. It's a bootstrapping definition based on the differentiability of the first derivative. Okay. All right, so let me just note, I'll make a connection with things that you know about, and maybe also shed a little bit of insight, a different kind of insight into the way you've looked at things previously. Okay, so we could equivalently, and so that's not obvious that this is equivalent, that's a theorem, but I'll just state it as a fact here. We could equivalently say phi is of class FCKF if FD K minus 1 phi is of class FC1. Okay, so again, this is a different kind of a bootstrapping definition. And the drawback to this one is that for its definition, it relies on these higher derivatives. So let me just indicate to you how these higher derivatives work. And then you'll see some similarities to things that we've talked about before. Okay, so notice that, right, so the first derivative, f d phi, is a mapping from O into L F U V. Okay, and so if you're working in a finite dimensional space, again, this is just the Jacobian matrix that you're familiar with from multivariable calculus. All right. Otherwise, it's a continuous linear map between these two normed spaces, but the idea is rather the same. Okay, so therefore, the derivative of the derivative, so FD2 phi, which is of course just FD phi. Okay, so what's this going to be, first of all? So this is going to be a mapping from O still, okay? And so the first derivative maps O into this normed vector space, right? So this vector space has the operator norm, okay? So this is a mapping from an open subset of a normed space into a normed space, Okay, so it's the derivative of the derivative is defined in the usual way. Okay, but I'm really here not concerned with what the definition looks like, but just in terms of what its domain and codomain is. And the codomain will be linear mappings. Okay, so the idea is that U is still U because O is an open subset of U, but V gets replaced with this is now the V. Okay, so it's U L F U V. Okay, so that's kind of tedious. But let's recognize this maybe as something a little bit more familiar. And it also maybe motivates why we talked about these multilinear mappings for the derivative before. Okay, so note. There. So I shouldn't write note since I'm already doing a note. Okay, so there is a natural correspondence between this space of linear mappings, which take values in the space of linear mappings. Okay, so L F of U, L F of U V, and the space of multilinear mappings, L2. Okay, so these ones will be bilinear because there's two copies of U. U V. Okay, so these are bilinear mappings from two copies of U into V. And let me tell you what that correspondence is. Okay, so if, what do I want to call this thing? Let's maybe call it little phi for the time being. Okay, so if I have a mapping phi in here, okay, so this is going to be a linear mapping into the space of linear mappings. Okay. So this corresponds to, and I'll just call it phi hat, which is going to be a bilinear mapping. And let me tell you how you define this. Okay, so phi hat is going to be a bilinear mapping. So it's going to take two arguments from U and give you something in V. Okay, so it's going to be U1, U2, and I'm going to define that in terms of phi. And basically, you do the only thing that you can. All right. So phi is going to take, phi takes U and gives you a linear mapping, right? So if I take phi and I apply it to U1, okay, then this will be a linear mapping in here, okay? And therefore, it will take an argument in U and give you something in V. So you write it like this, okay? And so in this way, you see that the space here in which the second derivative takes its values is not this kind of awkward looking thing. It's really the slightly maybe more comfortable seeming bilinear mappings from U into V, and these correspond to the derivatives in the way that we've talked about them before. We talked about the derivative as being symmetric and multilinear. Well, multilinear and symmetric. Okay. And so that's where this comes from in the setting of multivariable calculus that you have maybe seen before, but maybe you haven't seen this kind of stuff. because, well, when you take multivariable calculus, you're small children, and so you're not able to understand bilinear mappings that well. But now you're grown-ups, and bilinear mappings are well within the realm of things you're able to understand. Okay. And then this gets ratcheted on and on. And so let me just say, continuing in this way. So F, D, K, phi is a multilinear mapping. Okay. With from K copies of U into V. And this is just like we saw for not FDK, but for DK previously. Okay. And we saw that it was symmetric for DK, and it's similarly symmetric here. So you have to go and prove that. All right. And so this is how it corresponds in some way to the things properties of the derivative that we've seen before. Okay. What's going on in this case, which we do not have with our directional derivative, is when phi is of class FCK, this thing is continuous, and we do not have continuity of just dk phi as a mapping from O into this space. And I should be careful here. I mean, when I evaluate this at a point X. Okay. And so for our situation, we do not have the dk phi as a continuous function of X. Again, the reason being that spaces of linear and multilinear mappings do not have natural topologies. Okay, so that is a little discussion about FCK. And so again, this should be somewhat familiar to you. Okay, that's my note. So what do we want to understand? We want to understand the relationship between FCK functions and CK functions on normed spaces. Okay, so on normed spaces, we now have two classes of mappings. Okay, we have CKF, OV, and FCKF, OV. Okay, what's the relationship between these? All right. Are they the same? That would be nice. And by the way, I said that, you know now the answer is no. Okay, they're not the same, but they're closely related. Okay, so I'm going to state the correspondences in general between these two classes of mappings, and we'll only prove a little tiny bit of the stuff that I write down. The stuff that I write, the results that I state and don't prove are actually kind of hard to prove, you know, and kind of would take, you know, it's one of those things where it would take us 3 days to get through the full proof. The full proof is in the course text. Okay, so you can look at it if you want to, but we're only going to do a very limited amount of the proof. Okay, so Durham. So I'm using the notation above with U and V and O. Okay, and with that notation, I have two equivalent statements. And so again, what you would like to be true is that these two classes of functions are the same, but they're not. Okay. Phi, oops, phi is FCK OV. Okay, and then condition 2 is that phi is CK. And d phi, which we talked about before, okay, as a mapping from O into L, F, U, E is continuous. Okay. So remember the d phi. So let me just remind you. So we have the definition of f d phi. F d phi is defined by um, the fact that the remainder satisfies this equality. Okay, that's the definition of f d phi. The definition of d phi is not the same. It's quite different. So I'll just put that in a recall. The d phi is defined by d phi x applied to a vector u is d phi, our derivative that we've always been dealing with when we're dealing with functions of class C1 of x. That's the definition of capital D phi. All right, and the point is that this is defined by directional derivatives because this is the directional derivative at x in the direction u. Okay. All right. So the theorem has one last bit. Moreover, oops, I want that to be white. Moreover, if 1 or equivalently 2 hold, then FD phi and D phi are the same. Okay. All right. So this, what I'm going to do is I'm going to prove this for k equals 1. The proof is by induction on k, so we're just going to prove the first step in the induction. And unlike some induction proofs that we've done, and I've skipped over the induction step because the induction step is really just a repetition of the base part of the induction. That's definitely not true here. So I'm omitting a non-trivial part of the proof. And so I'll write something to that effect at the end. Okay, so we consider only the case k equals 1. Okay. All right, so let's prove this. All right, so we're first going to assume that phi is FC1. Sorry. I find my own video to be distracting to myself. And probably to you. All right. Okay, so we're going to assume that phi is of class FCK, and we're going to prove that it's of class CK, and that the derivative d phi is continuous. Okay. All right. Okay, so to show that it's of if it's of class FCK, then it's of class, sorry, if it's of class FC1, then it's of class C1. I have to write down the difference quotient and then show that the limit as t goes to 0 exists. Okay. All right, so the difference quotient is phi of x plus tu minus phi of x over t. Okay, and so here x is in O, U is in big U, and t is small enough so that the expression that I'm writing down makes sense. Okay, now by the definition of the remainder, this is f, and remember I'm assuming that it's of class FC, so the derivative FD exists. Okay, of x of tu. Okay, plus our remainder. This is just by the definition of the remainder. And that's, sorry, that's tu over P. Okay. Okay. So first of all, FD is linear, and so I'm going to separate the numerator into the two summands, and linearity of F ensures that this T will cancel with that T. So this is FD phi of X of U minus, okay, plus R, the remainder, like that. Okay, so I'm just going to do now a simple manipulation. So what do I know about the remainder? I know that the remainder um, uh, satisfies a condition like this. Okay, so I want to get the norm of U in there somehow. And so you do the obvious thing, you multiply and divide by the norm. Okay, so I guess for the time being, I'm assuming that U is not equal to 0 because I'm going to divide by the norm of U. Okay. All right, so this is going to be R P X T U over P U of U. Sorry, let's see. So I want the T is on the bottom. So it's P U, and then P U of U. Okay, and so Um, so this is certainly true if T is positive. So, right, so what am I doing here? So I'm using the homogeneity of the norm, okay, to take the T here and pull it out front. And when you pull it out front, it has an absolute value on it, okay? But I'm going to be taking the limit as T goes to 0, so it doesn't matter. But in order for things to actually agree, um, uh, sorry. Um, so I'm going to just first take T to be positive here. Just if it's not, then the difficulty is that this one's linear in T, and this one's not linear in T. It's linear with the absolute value. So the two terms here are treated differently. So just for simplicity, let me assume that T is positive, and then everything I write down is correct. And then you can kludge the case where T is negative in the same way. Okay. Basically you'll just get a minus sign here instead of a plus sign. Okay, anyway, I hope that makes sense. Okay. And so now, if you take the limit as T goes to 0, okay, of this, okay, so that's going to amount to taking this plus the limit as T goes to 0 of that, but the limit as T goes to 0 of this, because of the condition on the remainder, okay, so notice that the argument of the remainder and the argument of the norm are the same, that's kind of the point. As T goes to 0, this thing will go to 0, okay. Okay, so phi of X plus TU minus phi X over T is equal to F E P of X of U. Okay, and the point is that limit exists. Okay, and so because the limit exists, phi is C1. Okay, and moreover, this calculation, this one that we just did, shows that D phi of X U is equal to F D phi of X of u. Okay. And okay, so now this thing is a continuous function of x and u. Okay, and we proved that before. That's not just an obvious statement. I know that this is a continuous function of x. That's part of being FC1. All right. But that does not mean that when I evaluate it on a u, that the resulting function is jointly continuous in x and u, but it is, and we proved that before. Okay. We proved this. So let me write down what we did, what we proved to show that that's true, because the evaluation map, which I call EV, from L U V cross U into V is continuous in this case. Okay, and it's continuous specifically because U and V are normed. Okay, it's not generally true when U and V are not normed. Okay, does that make sense? All right, so that's one direction for k equals 1. So that shows it shows that that if it's FCK, then it's CK, and moreover, the derivative phi, okay, so let me write this as d phi of x of u, okay. So this also shows that d phi is continuous because d phi is actually equal, therefore, to f d phi, and f d phi is continuous because phi is a class FC1, okay. All right, good. All right, so that's one direction. And notice that this also shows that, oops, this also shows that d phi is the same as f d phi. Now, let's prove that if phi is of class C1, and if this thing, which is defined by that formula, is of class, is continuous, okay, then phi is of class FC1. Okay, all right, so okay. All right, so what do I need to do? So I need to prove, to show that it's of class FC1, I have that remainder condition. Okay, and I have to show that the remainder condition is satisfied. So again, I have to show that if the remainder is defined like so, then it satisfies that formula. Okay. Okay, so let's so because d phi is assumed to be continuous, that's part of the hypothesis in this case. Okay. If x is in O, there exists a convex neighborhood. So because this is a normed space, convex neighborhoods mean balls in the norm, but I'll just write convex neighborhood. And I'll just write it as O prime of x such that okay, so P V, P U V, so the operator norm applied to d phi of y minus d phi of x is less than epsilon. So I always do this. I never introduce the epsilon soon enough. Sorry about that. So I mean to include at the very beginning here let epsilon be positive. All right. Okay, and so this is just a statement of the continuity of d phi in the operator norm. Okay, and this is true as long as y is in O prime. Okay, so that's just continuity. All right, so it says that the d phi of y is within epsilon of d phi of x as long as y is in that neighborhood. All right, that's just a simple statement of continuity. Okay. So now, remember what I want to do is I want to show now um, uh, that I have the remainder equality. All right, so what I'm going to do is write down the remainder, okay, and then perform some estimates on it. Okay, so the remainder is phi of x plus u minus phi of x minus d phi of x of u. And I'm going to need more space here. Okay. All right. Okay, so that's the remainder. Okay, and that's the remainder with sort of the deviation away from x being now given by u. Right. And I'm going to look at the norm of that. Okay. All right. So now what I'm going to do is I'm going to rewrite these using the mean value theorem. Okay, so I'm going to take a curve that goes from x to x plus u, and I'm going to integrate the derivative along that curve. All right. So this is PV of the weak integral by the mean value theorem. Okay. So it's d phi of x plus, x s u, okay, ds minus, so here, I'm going to do this. I'm going to collect these two things together. So I'm going to go like this. Sorry. I'm not evaluating d phis here. Apologies. Okay. Plus SU. Okay. D phi of x. All right. Okay. So let me write it down and then I'll try to explain it. Okay, good. All right. So this term here just corresponds to this term here. And because, I mean, this term is independent of s, so when I integrate this from 0 to 1 with s, then I get that. Okay, so this term just corresponds to that. And then this term corresponds to these two terms by the mean value theorem. Okay, so I'm just taking these and I'm writing them as the integral from 0 to 1 of the derivative. Okay, so note that d phi of x plus su u is the same thing as d phi of x plus su of u. Okay, so that's the mean value theorem. You usually see it in terms of this, but I've written it in terms of that. Okay, good. All right, so now I'm going to take the norm inside the integral. Okay, and we saw how to do that, and you do it with an inequality. Okay, so this is the integral from 0 to 1 PV of, okay, so it's the same thing, d phi of x plus su minus d phi x of u. Yes. Right. Okay, so now I'm going to now estimate this thing using the operator norm. Okay, so let me just recall what the operator norm is. Okay, just so you can see where this step comes from. So the operator norm is PUV of phi, linear mapping phi, is sup over sup of PV phi of u, where u has norm less than or equal to 1. Okay. All right, so I'm going to apply that definition to this term. And I think I have my parentheses in the wrong place here, or I'm missing, let's see. So let's see here. I need an additional parenthesis like this. Okay. All right. Okay, so here, this is going to be less than or equal to sup, oh, sorry, white, not yellow. Okay, integral from 0 to 1, P, U, V, okay, of d phi of x plus s u minus d phi of x, okay, and then P, U of u. Yes, okay. So I've kind of taken and multiplied and divided by a norm of u, okay? Um, and so essentially I've replaced u with u over the norm of u, and so therefore the resulting thing will have norm less than or equal to 1, and I've pulled the additional norm of u outside, okay? All right. Okay, and so what you get out of all of that is, right, so this is less than or equal to, okay, the sup. All right, so now what I'm going to do is I'm going to sup the integrand over s, okay? Okay, and when you do that, okay, notice remember my assumption here. My assumption is that on this neighborhood O prime, the operator norm satisfies an equality like that. Okay, so I'm going to apply that to this term. Okay, right, so I'm going to get the sup over of P U V d phi of x plus s u minus d phi of x, and here s goes from 0 to 1, and then I multiply that all by pu of u again. Okay, all right, so I'm just taking the sup of the integrand over s. Okay, now I'm going to use this, and what I get is that this is less than or equal to epsilon p u of little u. Okay, all right, so what have I done? I've shown that for every epsilon, this thing divided by pu of u is less than epsilon. Epsilon times pu of u, right? So sorry, let me just write it down. So whoops. So pv of phi of x plus u minus phi of x minus d phi of x of u divided by pu u of u is less than epsilon, and this is true provided that u is in this neighborhood O prime. O prime. Okay. All right. So this shows that the limit as u goes to 0 of r phi x u over the norm of u is equal to 0. Okay. Because this is the remainder. Okay. All right. Good. So so that's it, right? So this shows that so thus B is of class FC1 OB. Okay, because I've shown that this is true for every X. Okay. And moreover, sorry, I should say because I still, in order for phi to be an FC1, I still need to show that what I've shown is I've shown that F d phi exists for every X, but I still need to conclude that it's continuous, but that's not hard because this shows that d phi is equal to F d phi, and I've assumed that d phi is continuous. Okay, so therefore, because the above shows that F d phi is equal to d phi, right? Okay, because in the remainder term, this is the continuous linear map that I get out of the definition of the Frechet derivative. Okay, and d phi is continuous by assumption. Okay, so that proves the result for k equals 1. Okay, so this gives the theorem for k equals 1. Okay. For k greater than 1, it is a difficult proof by induction. Using things that we don't know about yet. And also things that we're not going to know about at the end of the course. Okay, so I'm not going to do that. Okay, but the interesting thing is that it's true. Okay. All right, so this is okay. Sorry, I'll be back to visit that in a second. I know if you're taking notes that you hate it when I scroll like this. Okay. So this is sort of satisfactory. So you can conclude that being FCK is the same thing as being CK with a continuous derivative. What you'd like to be able to say can I conclude FCK from CK? So, I know that I can't conclude FCK from CK because I do need this additional condition of continuity of the derivative, and that's not going to be true, generally speaking. Okay, so there are counterexamples of things which are that are C1, but for which the derivative is not continuous. Okay, so therefore they're not FC1. Right, and those counterexamples are kind of complicated, okay, but nonetheless they exist. So you'd still like to know, without any additional assumptions on the derivative of phi, can I conclude FCK from CK in some way? Well, again, you can't do it from FCK. You can't do it from CK, but you can do it from CK plus 1. So another theorem, and this one I'm just not going to prove at all. So if phi is CK plus 1, then phi is FCK. And again, the proof is in the course text, and it's, again, it requires work and things we haven't talked about, right? Okay, good. So the point of the whole discussion so far in the lecture is that the calculus that we've defined is not exactly the same as the calculus that you have talked about before, okay? Um, in normed spaces. But in finite dimensional spaces, and that's really what you know about from your multivariable calculus course. So in normed spaces, in finite dimensional spaces, the two theories are equivalent. So I'll state that as another theorem, and then I'll chat my way through it. I won't give a full proof. I'll just chat about it, convince you that it's true. So if U and in fact, you only need here for U to be finite dimensional, but I'll stick to making the connection to the case that everybody's familiar with. So if U and V are finite dimensional, like say Rn and Rm, then Ck is equal to Fck. Mm-hmm. All right, so I'll just say a simple fact, which essentially is the proof, but you have to fill in some details. So recall that phi from O subset of, let's say, Rn, just choose F equals R for simplicity, because that's the case, again, that you will be familiar with. Is of class C K. And, so again, I'm not sure if in your multivariable calculus course you did this for higher derivatives, but certainly you will have done this for first derivatives, okay? But it's true for higher derivatives. So is of class CK if and only if all partial derivatives exist. So partial derivatives up to order K exist and are continuous. Okay, and so then you do some stuff. Okay, so like I said, you certainly would have seen this in the C1 case, right? So you would have seen that a mapping phi is continuously differentiable if it's Jacobian matrix. Okay, so Jacobian matrix is just the matrix of first partial derivatives. Okay, if the entries in the Jacobian matrix are continuous, right? You would have seen that in a multivariable calculus course, okay? And so that the analog of that for higher derivatives is also true, right? And so the theories that we have for differentiability are not necessarily the same for normed spaces, but they are the same for finite dimensional spaces. So that's good. So at least this agrees with the finite dimensional case that you're familiar with. Okay, but many of the interesting applications of these ideas are in at least infinite dimensional norm spaces, then very often in infinite dimensional spaces that are not necessarily normed. And so then the relationships between the calculus that we're doing and the calculus that you're familiar with is much more complicated than saying that they are the same. Okay, good. This is probably not exactly true, but it's true locally. Okay, we'll probably have to revisit some things about calculus that I could have talked about, but have chosen not to. All right, so um, um, we're going to talk about um, differentiable manifolds. Okay, so my understanding from what I read, and you all have told me about your background, not many of you, and possibly none of you, have a great background in just ordinary differential geometry. But the good thing is that the presentation of differential geometry that we're going to talk about here, except in some topics which will come significantly later, is really just exactly the same as it is for, what you would kind of call elementary differential geometry. So geometry of finite dimensional manifolds. We don't know what a finite dimensional manifold is at this point in time, but we will. And many of the examples that we're going to talk about are going to be finite dimensional, just because those are the ones that are the easiest to talk about, and really good examples of infinite dimensional manifolds require some build up to talk about. So it's not really easy to talk about nice examples of infinite dimensional manifolds. You need some stuff just to be able to talk about examples that are interesting. Okay, so what's the idea of a differentiable manifold? So the idea is you want to do calculus on curved spaces. So let me give you some examples of interesting curved spaces. These will turn out to be manifolds, although we don't even know what that word means yet. Okay. So there's what's called the n-dimensional sphere, which is written as Sn. And this is the set of points x in Rn plus 1. So that the Euclidean norm and it's important to what this norm actually is, because for different norms, it may or may not be a manifold, but for the 2 norm, it is. So this is the Euclidean 2 norm. Okay, and we talked about that a long time ago. Okay, so this is just, in for n equals 2. So it's okay, so that's some kind of a 3-dimensional thing. Okay, so this is n equals 2 for n equals 1. It's just a circle of radius 1. Okay. And I'll leave it to you to try to visualize higher dimensional spheres. Um, so spheres are a nice example of a curved object. Okay. Here's another one. Let's consider n by n matrices. Okay, which satisfy this relationship. Okay, so then when you multiply them by their own transpose, you get the identity. All right, so these are orthogonal matrices. That's the name for this kind of matrices. That's where the big O comes from. Okay, and so the interesting thing here is, for spheres, the relationship which describes these um, curved objects, so in the n equals 1 case, it's just x squared plus y squared equals 1, and then in the n equals 2 case, it's x squared plus y squared plus z squared equals 1. The point is that the equation that defines these things is nonlinear, right? So in that case, it has squares in it. And similarly, the equation that defines ON is nonlinear, right? We're taking a matrix and we're multiplying it by itself. So that'll, contain terms that are quadratic in the components of the matrix. So it'll be a nonlinear thing. And when you take the solutions of this equation, it's going to be some curvy shaped thing. Okay. It's quite complicated to understand what ON looks like in general. Um, um, but nonetheless, it turns out that this thing will be what's called a finite dimensional manifold. Right. So those are two finite dimensional examples. So let V be an inner product space. So this example generalizes this example. So my inner product space here need not be finite dimensional. Okay, but you can, here we just defined the n-dimensional sphere as a set of points whose norm is equal to 1. Okay, and this is because it's the 2 norm. The 2 norm comes from the usual Euclidean inner product, known in elementary school as the dot product. Okay, and I always make a point of saying to students that grown-ups don't say dot product. Grown-ups say Euclidean inner product. So don't ever use the words dot product again. Always say Euclidean inner product. Okay, so here we're using the Euclidean inner product, which defines a norm. And similarly, on a general inner product space, there's a corresponding norm, and you can consider the spheres for that norm. Be an inner product space, and note S of V to be a set of vectors in V whose norm is equal to 1. So that just means like that. Okay. So this is, if V is infinite dimensional, this will be a ball, not a ball, a sphere, the surface of the ball of radius 1. Okay. All right, so these are kind of examples of curvy things that we'd like to be able to do calculus on. The only thing we know how to do calculus on now are open subsets of locally convex spaces. And these are somehow, vector spaces in your mind. You can somehow imagine those as being flat. And so you'd like to be able to adapt what we've done in vector spaces to spaces that are not, don't have any kind of vector space structure. Okay, so one of the things you notice is that in all of these examples, so I said these things satisfy nonlinear equations that define them, that equation, and that equation, and that equation. And as a result, none of these things are subspaces of a vector space, right? This is not a subspace of Rn plus 1. This is not a subspace of the set of n by n matrices, and this is not a subspace of the Hilbert space V. Okay, these are curved things. Okay, all right, good. So that's the point of differential geometry. All right. So what do you do to try to do calculus on spaces like this? Well, you do kind of something quite naive. And again, this idea will be familiar to you from courses like vector calculus, because you talked about surfaces in vector calculus, because you would have talked about Stokes' theorem and Gauss's theorem and flows through the boundary of a surface and things of this nature. And how did you, and then you did some integrals, right? So you were integrating over these surfaces. And how did you do those integrals? Well, you did those integrals by parameterizing the surface. And so essentially what you're doing when you are parameterizing a surface is you're taking a chunk of that surface and you're making it, and if it's a two-dimensional surface, you're making it look like an open subset of two-dimensional Euclidean space by the parameterization that you've chosen. And so the idea of a manifold in general is that locally, so around every point, you make it look like an open subset of some locally convex space, and because you can do calculus on the locally convex space, it means on that little subset of the manifold, you can do the same kind of calculus on that just by doing it in the locally convex space. And the issue that arises is you want to make sure that if you parameterize things in a certain way and somebody else parameterizes things in a different way, that you both are actually doing the same thing. Okay, so that's kind of what differential geometry is. Okay, now, so that's all just nonsense, of course. Let me try to be precise. Okay, so so there appears at the beginning of this theory just kind of a long list of definitions. Okay. All right. So first, let me introduce some terminology. Um, so let's let U V be LCSs. Let N, let's say, in U and O in V be open. And let phi map O N into O. All right. So phi is a CK, right? And so K is some positive integer, could possibly be infinity. Okay, so it's what's called a CK diffeomorphism. If it is a CK bijection. Okay, so it's 1-to-1 and onto, and it's of class CK. And so because it's a bijection, it has an inverse, and it's to be a CK diffeomorphism, I require the inverse to be also CK. Okay, so there'll be homework problems where you can explore this definition. Okay. All right, so now let's parameterize some sets with subsets of vector spaces. Okay, so again, the picture you should have in the back of your mind is things that you did in vector calculus with parameterizing surfaces with two coordinates. Okay. So we're going to start with something very floppy, just a set. Okay. So I'm not going to write this every time. So I'm going to talk about CK, and sometimes I'll use R instead of K, and I'll be kind of inconsistent about that because sometimes you want to use both of them. So I'm going to mix them up in inconsistent ways, and I apologize in advance for that. Here I'm going to use R. Okay. All right. So the first thing I'm going to define is what's called a chart. Okay, so a chart for S is three things. Okay, so it's a triple, which I'll have U phi, phi, and V phi. So let me tell you what those things are. So V phi is a locally convex space. U phi is just a subset of S. Okay. Uh, okay, and then three. Phi is a mapping from U phi into V phi. And so you'll notice here that I'm trying to carefully use a different font for the U here. When I had a vector space, I wrote U like that. Here I'm writing U like that. Okay. So bear in mind, so although this is U and we just spent a month talking about U as a vector space, this is not a vector space. No, sorry about this. There, just want to get rid of that H. V. Okay, so what do I know about phi? So it's a bijection onto its image. So it's injective. Okay, so that's all a chart is. And so again, you should think of, so let me draw a picture of how you should think about a chart in your mind. So you should think of S as being like some curved thing. Right? And U phi you should think of as being an open set, is how you should think about it. I haven't said what open set even means, so take that with a grain of salt. Right, and then I have a vector space over here, so I'm going to draw a vector space like that. Okay, this could possibly be infinite dimensional. I'm drawing everything like it's two-dimensional, so the picture is very non-representative, but it gives you a picture. Okay, and then the mapping phi goes like this, and it's a bijection onto its image. Right, so this is okay. So this is phi of U phi. Okay. So that's all a chart is. And so, the name I think is suggestive, right? So a chart is, like a map from cartography. And what does a chart do in cartography? Well, it just takes a section of the surface of the Earth and it maps it into some flat space. Okay, so that's all a chart does. Okay. All right, so that's kind of the parameterization part. So now what you need to bookkeep is you need to bookkeep the part where what if there are two charts? Okay, so you come along and you choose a parameterization of the Earth's surface, and I come along and I do a different kind of parameterization of the Earth's surface. How do we know that we're doing things that are consistent with one another? Okay, so this is the notion of compatibility of charts. Okay, so charts. Oops. U phi, phi, v phi, and U psi, psi, v psi are compatible. Um, and here's where I use K, or sorry, not K, I guess I'm using R here. So C, R compatible. And we'll see where the R comes from. If, okay, so some things hold. Okay. Right, so first, so I'll draw a picture that encapsulates this, but I'll write the definition down first. So first, so really in the definition makes sense if U phi and U psi do not intersect, but you should think in your mind of these things intersecting. So if they don't intersect, then their intersection is the empty set and the whole definition becomes vacuous. So definitely have in your mind that these things overlap. Okay. All right. So the first condition is that when you take the intersection and you map it by the chart maps phi and psi, those are open subsets of the vector spaces. All right, that's the first condition. Okay, so I can count. All right, so then there's this mapping called the overlap map. Okay, and the overlap map is best envisioned with a picture that I'm going to draw in a second. Okay, but I'll write down the definition first. So the overlap map is psi composed with phi inverse. Okay, and this is going to be a map from this thing into this thing. Okay, so it's from phi of u phi intersect u psi into psi of u phi intersect u psi. Okay, and it takes a point, let's say here, which I'll call x, let's say, and maps it to psi phi inverse of x. Okay. All right, so this is the mapping, and the requirement for compatibility is that this mapping is a CR diffeomorphism. All right, so it'll certainly be a bijection. Okay, it'll be a bijection because each of phi and psi are bijections onto their images. So basically what I'm doing when I'm composing these things is I'm composing two bijections. Okay, so it'll certainly be a bijection. And so the content here is about the differentiability of this thing. Okay, so the picture you should have in your mind is like this. So I have two charts, U phi and U psi that overlap. Okay, so let's patch these like this. Then I have phi, which maps into V phi. Psi, which maps into V psi. Oops. Psi. All right, and this one I hatched like so. Okay. Now, this is the intersection here. Okay, and that I have required so that when I take the image of the intersection under the chart maps, phi and psi, that's open. Okay, so I'm going to get these regions here. And let's say here. Okay, which are open subsets of V phi and V psi. Okay, and given a point in the image of the intersection here, which I'll outline in red here, and I don't know why it chose to do that. Okay, that is going to map to the image here. Okay, so this map here, which maps the red bits to the red bits, is the overlap map. Psi opposed with phi inverse. Okay, and we require that thing as a mapping from this one into this one. We require that mapping to be a CR diffeomorphism. So as I said, it's always a bijection. Okay, so it's the diffeomorphism part that has the content. So it's CR going in both ways, right? So it's CR from here to here, and then its inverse is also CR. All right. Okay, so that's the definition of compatibility. All right, so I think I'm kind of at the end of the lecture for today. And so we'll pick this up next time and see how to turn these two bits of the definition into a structure for the set S. Okay, so you're welcome to go, and I'll hang out if anyone wants to ask a question.